Semiclassical gravity is an approximation to the theory of quantum gravity in which one treats matter and energy fields as being quantum and the gravitational field on the other hand as being classical. So we have quantum fields together with a background which is the gravitational field, which is a classical background. Now, in general, if we want to consider a quantum theory, we start from a classical action, which we define as S, and this classical action depends on fields. So it contains, for example, the gravitational field, g mu nu, and other fields that we simply label as phi. In semi-classical gravity, this term here remains classical, whereas this term here becomes quantum. And one way to express this is by using path integrals, for example. So when we have an action, we multiply the action by the imaginary unit, then we take the exponential of such an action, and if, for example, we want to integrate out such fields, we have to integrate over the field phi with some measure d phi which contains all the fields at different locations. So in principle, we have an infinite amount of differentials, of a product of differentials. So it is not so trivial to define a path integral, especially if you want to do it formally, but intuitively this can be understood without major difficulties. Let's assume that everything is well defined. Once we carry out the integration, we get rid of the field phi and we obtain the so-called effective action. So we can rewrite this as an exponential of I gamma, which depends only on the field g mu nu, on the gravitational field. Let me try to write this properly. So g mu nu equal to this. And performing such a computation means basically that we are averaging over the field phi. So we are integrating over all the possible values for phi or the possible configurations for phi, and that will give us this so-called effective action. This is also known as the back reaction of quantum fluctuations of matter fields on gravitation. It's some kind of averaging performed over quantum fluctuations. Now, at this point, we can also take into account the energy momentum tensor in general relativity T alpha beta of x is given by the following formal expression: 2 divided by the square root of minus g, and then we have the change in the action, g mu nu phi, so it's this action here, and we take the variation with respect to g alpha beta, the inverse metric tensor. So by defining the energy momentum tensor like this, one derives the well-known Einstein equations, Einstein field equations if you want. Now, in quantum field theory, we can define an average of the energy momentum tensor operator. So we define this operator, T alpha beta of x, and its average is given by an average performed over path integrals. So we have a ratio of path integrals. In particular, we have T alpha beta of x exponential I s g mu nu phi. So let me just write g for the sake of simplicity, d phi, and this is divided by the same integral but without this factor of T alpha beta here. So we have integral exp is g phi d phi, like this. Now notice that what we have in the denominator is basically just the exponential of I gamma that we defined previously up there. And you can notice that we can rewrite this as the exponential of minus I gamma, like this, and it is basically just this term here. And since we can write T alpha beta in this fashion, so you can see that we have a derivative of this action inside the integral, you can see that we can rewrite this as 2 divided by I, a factor of I, square root of minus g, and then we have this derivative, this functional derivative of the exponential of I gamma. So if we rewrite that as a derivative of the exponential of I gamma, you can see that when you take the derivative, this factor of I will cancel, and when you take the derivative of this quantity, which is the exponential of I gamma, when you take the derivative, the functional derivative of s, the functional derivative will appear here. It's due to the chain rule when you take the derivative of the exponential. The derivative of the exponential is the exponential itself multiplied by the derivative of the argument of the exponential. So this is the formula that we get. And this can also be written more simply like this: 2 divided by the square root of minus g, the functional derivative of gamma with respect to g alpha beta. So g alpha beta depends on x if you want, and gamma contains g mu nu, the g's, so the metric tensor. It depends on the metric tensor g mu nu or g alpha beta, whatever. Now, at this point, you can see that we have the usual formula that we see in general relativity, where instead of the action, which contains these quantum fields, we just have the action which contains g mu nu, so the metric tensor. And if we use the well-known Einstein-Hilbert action, this will simply give us the well-known Einstein field equation. So what we are going to get is something proportional to R alpha beta, the Ricci tensor minus 1/2 G alpha beta, and then we have the Ricci scalar. So we're going to get something like this, and the proportionality between this expression and this expression here is the usual coefficient 8 pi g divided by c to the fourth if you keep all the units. And for example, if you choose units such that c is equal to 1, then of course you just have 8 pi g and so on and so forth. It depends on the units that you want to use. And then this multiplies, of course, the average of T alpha beta, and this must be equal to this object here, which sometimes is denoted as G alpha beta, which is the Einstein tensor. So this is defined as R alpha beta minus 1/2 G alpha beta R. So this is a semi-classical gravitational equation, because you can see that we are averaging over this quantum operator, whereas on the right we don't have any quantum operators because we are considering g mu nu just like a classical background, so we are not quantizing gravity, but there are some quanta here hidden under the rug because we have quantized this energy momentum tensor.